Okay, let's work out number 37 up here. At the end of an advertising campaign, weekly sales of smartphones declined according to the equation y equals 12,000 times 2 to a certain power. So number 37, they give us the formula for decay. Y equals 12,000 times 2 to the negative 0.08 times x. 2 to the power negative 0.08x dollars. Where x is the number of weeks after the end of the campaign. A, determine the sales at the end of the ad campaign. Part B, 6 weeks after the end. So, at x equals 0, we would substitute, and in place of x, I should be writing 0. So the exponent is this negative decimal times 0, which is just 0. 2 to the 0 is 1. And right, we should have our original $12,000 in sales at the moment the sales campaign ends. Now, what about after 6 weeks? X equals 6. So y should equal 12,000 times this. In place of x, I have written 6. Okay, let's get the calculator out and tap on that. When all the tapping is done, we get $8,603 plus 73 cents. I'd hate to have to figure that out without a calculator. Then they ask us, does the model indicate that sales will eventually reach 0? No, because this is an exponential function. It's going to be asymptotic to the x-axis, but it never gets there. Okay. Our last topic is something that's kind of magic. There's that number pi, right? Pi is a very magical number. It was invented, about 1000 BC or so, way BC, by the Greeks. The Greeks knew about this. And pretty much everybody's aware that pi is approximately equal to 3.14. But the decimal places go on forever, and no pattern ever repeats. The fact that no pattern ever repeats means that it cannot be expressed as a fraction of 2 integers. And therefore it's an irrational number. We also say that about pi. And what pi was, and by the way, since it can't be represented as a fraction, you oftentimes see pi approximated by 22/7, but again, that's an approximation. That's going to give you a repeating decimal when you convert this to a decimal. And it's close to this, but it's different. Just an approximation. Pi is the ratio of any circle to its diameter. That's why the Greeks got interested in it in the first place. Well, many years later, in the 1700s in Switzerland, there lived a man named Leonhard Euler. I guess in German, he was Swiss, I think he spoke German, his name was German. In German it would be pronounced Leonhard Euler. And he discovered the number E. And E is one of those magic numbers like pi. It's approximately equal to 2.71828. I think in your book they show you the 1828 next. It just so happens by coincidence the next four digits are 1828. And that's an unfortunate thing to show you because it kind of suggests that there's a pattern that's going to repeat, but that doesn't happen. There will never be a repeating pattern. It's one of those irrational numbers. And E is sometimes called the exponential number, or sometimes it's called Euler's number. His last name began with an E, because in German the EU is pronounced Oi. So Leonhard Euler, the Swiss mathematician, discovered this 3 centuries ago. And it's so important that this number gets its own key on a scientific calculator. On a scientific calculator, you'll see that key, e to the power x. And that's a function. If you say y equals e to the x, that declares a function. And that function has some really special and useful properties. For those of you who go on to calculus, you will see some of those remarkable things that e to the x does. Let's read example 7. This is on page 322. And let me preface it by just saying this. In the previous problems that we just looked at today, we were dealing with interest that was calculated once a year or once a quarter. We were looking at inflation rates that were figured out annually, or something like that, but over fixed periods of time. Now you may have heard, you may have seen in advertisements for bank accounts, they tell you, oh, if you get this, take out this account here, you get this continuously compounded interest. That means it's not compounded at once a year, or once a quarter, or once a month, or even once a day. It's a continuous thing, continuously compounded. Let's look at example 7. Growth of an investment. If $10,000 is invested for 15 years at 10% compounded continuously, what is the future value of the investment? Well, to do continuous interest, continuously compounded interest, you use this formula. P is the principal. E is Euler's number. R is the interest rate. T is the amount of time that we're going to let the interest accrue. So, in number 7, we have $10,000 invested for 15 years at 10%. So principal is $10,000, and we write down the number E. The interest rate is 10%, and we multiply that interest rate by the number of periods of time. So that's 10% over a period of a year, and then it's over 15 years. But don't be confused here. Just because I said over the period of a year, it's going to be compounded continuously. Okay, we're going to need to know what is e to the power of 1.5. If you have that key on your calculator, it's pretty easy. Otherwise, you're going to find yourself typing this in, and then, well, if you don't have a way to say 1.5 is the exponent, you're going to have to use the fact that 1.5 equals 3 over 2. And this means cube the number and then take the square root of that. Can be done with a regular calculator. You don't have to have all the fancy bells and whistles. But if you have all the bells and whistles, or even if you don't, you're going to arrive here. After 15 years, your $10,000 will have turned into $44,000, $44,816.89. So, good to know about continuously compounding interest. Good to know about E, the number E, and we'll see it later in the semester, and we'll have a little bit of homework with it tonight. So for your homework, go to my math lab, and there will be an assignment named 5.1 video. It actually will contain a video and then an animation where you can play with the numbers and cause curves of exponential functions to move around as you change the numbers. So it's pretty educational and entertaining. Then back in the toolbox homework on page 312, just work at 19, 21, and 27. That's a little bit of practice with scientific notation. And then for section 5.1 on page 323, 1, 7 through 17 odd, 31, 39, 41, 45. Thanks.